Hey guys, welcome back to Zenkayya. So in today's video we will look at cryptography part 2. Alright, so in the last video we have seen cryptography part 1. We have studied about symmetric and asymmetric cryptography. Alright, so in this today's video we will look the further topics. Alright, so let's start. First of all, why use asymmetric cryptography? Alright, what is the use of asymmetric cryptography? So in last video, if you remember, symmetric looks like something like this, where Alice is sending some message to Bob and it will pass through this encryption method and decryption method. In their shared secret key will be there, that is common to both encryption and decryption, right? So this is nothing but symmetric encryption, and in asymmetric encryption it is nothing but two keys will be there, that is Alice will be sending to Bob and it will be Bob's public key and Bob's private key. Alright, two keys are involved in it. That is why it is known as asymmetric encryption. I hope you remember it. If you have not, if you don't remember it, just go through it, the previous video, and I'm sure you will get it. Alright, so let's start today's video. In today's video, we'll understand the importance of asymmetric cryptography. Alright, what is the need or what is the use of asymmetric cryptography? First of all, you need to understand that symmetric and asymmetric both are used in the encryption method. Alright, so how it is used? Here you can see symmetric encryption is fast, as we have seen that it is both public key, both keys are same, and in order to exchange the data it is both fast, but exchanging key securely is challenging, right? Imagine you need to send message to your friend and you have to keep the key secret while you are sending it in public. That is the main challenge here. So symmetric encryption is fast, but it has one challenge, that it is not secure. How to make it secure? In there, asymmetric encryption comes into play, that is, it is slow but secure for key exchange. Alright, solution. So what is the actual solution that works in the whole internet while doing cryptography is use asymmetric encryption to negotiate the symmetric key, then switch to fast symmetric encryption for the rest. Alright, so for exchanging the key you can use asymmetric. Once you exchange a key, then you can use the symmetric encryption. Alright, that is how you use both symmetric and asymmetric. Let's understand it more by example. Alright, so imagine an analogy I'll give you so that you can understand the whole framework. So first of all, you have to send one box to your friend. Alright, box with a lock. That lock, you have the key. Only you have the key. Your friend can't open it. Alright, so you are sending that box to your friend. So in there, your friend will send you the secret instruction. Alright, so you ask your friend to send you a lock, only they have the key. You place the secret in the box. So basically, imagine I am there, I am sending the box to my friend. My friend will send me the secret key in that box. Alright, and that box have a lock. That lock key is with me. Only I can open the key. So I will give the box. My friend will put the secret key in there, it will lock it, and then it will send me. Alright, then I can open with the lock with the key, and then I can see the secret message. That is how the whole encryption or decryption works with symmetric and asymmetric. Alright, that is the analogy that you can understand. So now both of you can communicate in secret with that shared code. So only me and my friend knows the shared code. Alright, now nobody knows it, as because that key has been shared to me secretly, right? That is the whole point of asymmetric key. Now let's see some analogy. Secret code, encryption, symmetric encryption plus cipher plus key. Alright, secret code is not that, is symmetric key, cipher plus key. Alright, lock, what is lock? It is public key. Lock key is private key. Box is nothing but encrypted transmission channel. Alright, so here these are the analogy that you can understand. Alright, so once you reach the secret code, that is nothing but symmetric encryption. All right, but before reaching the key, that lock and locks key, that is public key and private key. Box is what? That is a transmission channel through which you communicate. All right, I hope you have understood. Now real world analogy, let's look at real world key exchange, how it is used in real world application. In practice, the process is used in TLS. I'm sure you have heard this particular term called TLS, that is HTTPS and VPNs. So I'm sure you have heard these terms called VPNs, TLS. All right, so public key is silently sent openly. All right, the public key, that lock, is sent openly. Private key is what? Locks key is kept secret by the server. So server will keep that locks key, that is private key. All right, once the symmetric key exchange securely, all further communication is fast and encrypted. So basically you need to send that key securely. Once that key is sent securely, then you can communicate with that communication, that is fast and encrypted. All right, but there's a catch. How do you verify the person you are talking to is a real one? All right, that is the real catch. Let's see how to do it. What is RSA? So basically RSA, Diffie-Hellman, these are different algorithms that we will be looking forward. All right, in today's this topic is known as RSA. RSA is a public key encryption algorithm. So let's understand how RSA works. It enables secure communication over insecure channels. All right, so based on mathematical difficulty, factoring large numbers. So basically the main reason or the main logic behind it is factoring large number, that is mathematical difficulty. All right, the computer finds it more difficult or time taking process in order to find factoring large number. All right, even if an attacker interrupts the communication, they can't decrypt it without the private key. All right, this is the whole logical reason behind it. All right, let's see now what is the further reason behind it, the math behind RSA security. Let's see. So first, easy. What is the easy part? The easy part is multiplying two large prime numbers. That is quite easy. All right, multiplying two large numbers. Now what is hard? The hard part is factor their product to find the original primes. That is, find the factor their product to find the original primes. All right, finding factor to factor their product to find the original primes, that is important, and that is difficulty in nature. All right, let's understand. So imagine two numbers are there. So this is one number, a big number, and this is another big number. Now this number, if you multiply, this will again come as a large number. All right, now multiplication is an easy part. What is difficult part? That is factorization. Computationally hard, it is, computer find it's hard to factor it, right? Factorization. Real RSA key uses 300 plus digits prime. That is the main thing, that it uses 300 plus digits prime. You can imagine how long it will be and how much time taking process is to find the factors of each and every number. All right, 300 digits number, one by one you need to find the factors. That is quite practically impossible to factor. All right, that is the whole point of cryptography, to make it more difficult so that other people finds it difficult and they should not be able to decrypt it without having the secret key. All right, so this is the whole nature. Now how RSA works, key generation, let's see it. So imagine first you have to choose two prime numbers, all right, P and Q, let's say. Then compute N equal to P into Q. All right, so first you find the multiplication of it. After that you need to find phi of n. What is phi of n? It is a function. What is the function formula? It is P minus 1 into Q minus 1. Once you find the phi of n, you will have some value. All right, what is that value? After that you have to choose two keys, that is E and D. All right, E is nothing but GCD of E and that phi equal to 1. So basically co-prime of E and that phi, two numbers are there, both co-prime should be 1. Basically no common primes are there, or no common factors are there. That is the what meaning of GCD. All right, find D such a way that E into D modulo phi of n equal to 1. All right, after that you need to find a number in such a way that if you multiply E into D and then if you divide it with phi, the modulo, that is the remainder, should be 1. All right, so you need to find a number E and D in such a way that this particular condition should be true. All right, so now observe here encryption with public key. That is, imagine you have one message. What is the message? Message is M. All right, you have a N. What is N? N is modulus. N is modulus means N is that value, P into Q. All right, P into Q is N. All right, so now M is a message that you have done power, M to the power E. What is E? E is that encryption code. All right, E is nothing but here, E is that code number. So M to the power E modulus N. So once you do it, then you will find the C. What is C? C is ciphertext. What do you mean by ciphertext? It is the encryption code. Imagine if someone gets C also, they won't understand what is the M. M is nothing but message, right? So now in order to decrypt it, you need to read it, right? You need to understand it. So you need to decrypt it. How would you decrypt? It is, the formula is C to the power D mod of N. Then only you can find the M value, actual M. So until and unless you know D, and until and unless you know N, and until and unless you know the C, you can't find the output. All right. And if you try to find out this D, it will be taking a lot of time. That is impractical in nature. So that is, you need to know D, you need to know E, then only you can find the real message. That is the whole point of RSA. All right, that is the whole point of encryption and encrypting and decrypting. All right, I hope you have understood this. Now imagine, we'll see with an example. P is 157, Q is 199. Now N into both, if you multiply it, N will be 31243. Phi of N, that is P minus 1 into Q minus 1, it is 30888. Now imagine E is a 163 and D is 379. It can be any random number, but the condition should be true. Now encryption, if you do encryption message, imagine I need to send a message 13. All right, that to my friend. How do you send it? C equal to M to the power modulo to the power 163E. Modulus of this actual N. N is 31243. You will get one number. All right, that is ciphertext. No one can understand. By looking at this number, you won't understand this is 13. The actual code is 13. All right. So while decryption, what you will do, take this number to the power 379 modulus of N, 31243. Then you will get 13. All right, that is how you get the actual secret code. So if you don't know E and if you don't know D, it can't work out. All right, that is the whole point of RSA. So after that, you can message successfully decrypted. That is how you do decryption. All right, so some common RSA terms are P and Q are prime numbers, N is product of P and Q, E is nothing but public exponent, even public, that will be going publicly. All right, private exponent, D is only known by you, it is the key. Okay, private exponent. M is nothing but plain text message. C is ciphertext. All right, this is the common symbols that you have to know in CTFS also. All right, CTFS are some challenges in the hacking terms. All right, what is Diffie-Hellman Key Exchange? Now we have seen RSA. Now let's see Diffie-Hellman Key Exchange. What is exactly this method? A method to establish a shared secret over an insecure channel. All right, so over an insecure channel, we need to send one shared secret without having any prior shared secret. All right, that is a challenge. So shared secret used later for symmetric encryption. No need for asymmetric encryption. No eavesdrops can compute the key. All right, let's see how it works. So imagine Alice and Bob's pick. This is a very interesting analogy. Watch it. Alice and Bob's each picks a secret color. Imagine it is red and imagine it is blue. Okay, red and blue. They both start with the same public color. All right, so now they will choose one public color, that is, let's say green, okay, red, blue and green, mix their secret code with public colors. So red and green, blue and green, some color will come up. All right, so exchange the results. So whatever the results they are getting, they will exchange. Both doesn't know what is the actual color, so whatever the new result came, it will exchange with the other, and whatever new result came, it will exchange with the others. Then mix received color with their own secret key. So they will mix the received color, the new color they have received, with the secret again. So it will mix with the red, it will mix with the blue, so that they get the actual same final color. But they don't know what is the other's secret key. All right, they just know they have shared the secret key and they will find the color. So but no one watching can reverse engineer their secrets. All right, no one will know what is the other secret of the other code, the other person's code. All right, that is how Diffie-Hellman works. Let's see with an example. Public variables, imagine p equal to 29, generator g equal to g is nothing but 3. All right, two numbers are there, 29 and 3. Secrets are nothing but Alice has picked up a, that is equal to 13, Bob's pick up b equal to 15. All right, let's see how it works. So imagine this is an algorithm. Alice a equal to the formula. What is the formula? G of a mod of p. So a choose 13, right? So a have choose 13 here. So it is nothing but 3 to the power 13, right? A is nothing but 13. 3 to the power 13 modulus of 29 equal to 19. All right, so the new color they got is, Alice got is 19. B have done the same thing with the formula and got 26. So 19 and 26 are the new colors. All right, but the actual number was 13 and 15. All right, they exchange this public key. So they will exchange 26 and 19. After that, what they will do? After that, they will compute with 26. B is 26 and computes b equal to a mod. They will do this particular formula and they got 10. Okay, then Bob's also receives the same thing, 19, and does the same operation formula, and it also finds 10. So both are now sharing the secret key, that is 10. Only both knows. All right, but both doesn't know what is the actual key. All right, that is the whole point of Diffie-Hellman. All right, so public values are p, g, a, b are visible. All right, but computing the shared secret requires solving discrete log problem that is difficult in nature. Eavesdrop cannot calculate the secret even if they see a and b. All right, even if they find p, g, a and b are visible, but they can't find this last common code. All right, that is how this has been designed. So I'm always amazed by how people used to think all this or find this kind of formula. I respect those scientists. All right, so real world's use of Diffie-Hellman used for RSA and other protocols. So RSA is used for digital signature and authentication. All right, Diffie-Hellman for secure key agreement. Example: TLS, SLS, SSL, HTTPS and SSH BPNS. All right, these are different example where they are being used in real world applications. All right, so the bonus point is DH plus RSA equal to strong security. All right, so Diffie-Hellman and RSA, if you use both, then only it becomes the strong security. Diffie-Hellman generates the shared key. RSA authenticates identification, prevent MITM, is man-in-middle attack. TLS combines both for secure communication. All right, that is how the security works, both symmetric and asymmetric, both combines in their own way, so that they can share the secret key and they can authenticate also while during passing the code. That is how it works. Now, why do we need a term? One beautiful term is there, that is called digital signature. Let's understand about this. All right, now digital signature is not that signature that you give during any exchange of information. All right, this is a different digital signature when you use it when you visit some website, or when they will authenticate whether you are a correct user or not. Alright, in the physical world, we sign documents to approve transactions, acknowledge receipts, and agree to terms. Alright, but let's see how digital world works. But in the digital world, signature needs to be secured, tamper proof, verifiable. That's where digital signature comes in. Secure means it have to be secured enough. Tamper proof means people should not be able to change it. All right, it should not be mutable, kind of changeable. Okay, it should not be changeable. Verifiable, whether it is verified or not, it should be verifiable. That's where digital signature comes in. Alright, that's where digital signature comes in. Let's see how it works. So proves authenticity, integrity. So who signed it? Unchanged content based on asymmetric cryptography, signed with private key, verify with public key. Digital signature is equal to legal proof in many countries. Alright, let's see how it works. So imagine how it works. Conceptual flow. Sender hashes the document. So imagine I want to send one document to my friend. I will hash it. Hashes means, for now you can imagine it as encryption. Okay, so sender encrypts the hash with their private key. All right, so with private key I will hash it. This is the digital signature. Alright, this is the digital signature. Now sender sends the original document, encrypted hash. Alright, encrypted hash and digital original document. So original document will be with the encrypted hash. So now receiver hashes the received document. First it have to hash, right? Hashes means kind of decryption. Then decrypts the signature using sender's public key. Alright, so I have hashes with the private key. Alright, so now decrypts the signature using sender's public key, the other person, and compares both hashes. So now it have to compare whatever I am sending and what is the original one. It hashes match, then document is authenticate and intact. Alright, that is how they verify the digital signature, whether it is correct or not. Alright, so what is not? Common confusions are there. What is not? Let's see it. Electronic signature is not equal to digital signature. Don't confuse. Whatever you sign it and give it in documents, those are not digital signature. Just passing an image of your signature can be easily copied or forged. Alright, can be easily copied, that's for sure. Doesn't verify who signed it or if content was changed. Digital signature is equal to proven identity plus verified content. Alright, both have to be there, proven identity and verified content. Now let's talk about certificates, proving identity online. Alright, some website needs to identify you, right? Whether you are a trusted person or not. How do they do? Digital certificates link your public key with your identity used in HTTPS to verify websites. Alright, so it links your public key with your identity that is used in HTTPS. Alright, HTTPS used by the websites to verify different websites. Trusted by browser through certificate authority, also known as CAS. Alright, chain of trust. Imagine chain of trust. Your site. So basically your site is there. Alright, imagine you have a website. Intermediate CA will be there, that is certificate authorities again. Then it will be connected to root CA, again one main root CA will be there. Then what browser will do? Browser trust root CA and CA trust intermediate CA and your site. Okay, and likewise your site is also trusted. Alright, so first browser trust root CA means root CA trust intermediate CA means ultimately browser trust your site. Alright, that is the flow it is flowing through. I hope it is clear. So let's see an example. HTTPS and certificates. You open one website called, let's say, newdeck.com. Alright, browser checks certificate. So first browser will check the certificate. Is it valid or is it signed by a trusted CA? Alright, if yes, secure connection will be established. So whenever you open a website in your browser, it will check the certificate. Is it valid? Is your digital signature valid? And if it is valid, is it signed by a trusted CA, that is certificate authorities. If yes, secure connection will be established, right? TLS ensures three things: confidentiality, integrity, and authentication, that is CIA triad. All right, we have seen it in the earlier classes. So how to get a TLS certificate? There are certain ways to get TLS certificate. First, paid one, you can go in a site of DigiCert, Global Sign also. All right, some free options are there. Let's Encrypt, if you go, then also you will find TLS certificate to identify yourself, all right, or to create a digital signature. So you can use these various different options. For domain you own, easy setup, widely trusted, modern website must use HTTPS. All right, some suggestions are given. All right, so some common attacks are there, methods are there that can be used. So first is brute force attack. What is brute force attack? Try every possible key, password, guaranteed success eventually, but it takes time. Brute force attack is like try every possibilities. All right, imagine someone is trying to open your Instagram account through all the possibilities of password. It is possible, but it will take huge time. All right, time consuming and resource intensive. Dictionary attack. What is dictionary attack? It is similar to brute force attack, but it will try some common and likely password, okay, from the dictionary. It has a lower amount of possibilities in comparison with brute force attack. All right, that is how people may attack. Now next is hashing, that we will see it in the next class. All right, what is hash function, what is useful in security, and all, will be looking at it in the next class. All right, with this we have completed part 2 of cryptography. I hope you are understanding and enjoying it, and make sure, don't forget to like, subscribe, and share it with your friends. Thank you.